Propose a very simple algorithm which I'm going to claim solves the interpolation problem. What's the interpolation problem again? We're finding some relaxation of the minimum cut. When this relaxation of the minimum cut is as follows, we find the arg minimum in Rn rather than -1 and 1 of the cut between two things squared weighted by Wij subject to label constraints. We say that some vertex I1 has its label forced to be Y1 and some vertex IL has its label to be forced to be YL, where Y is some value in -1, 1 to the L. As soon as we have a single constraint, we have if the graph is connected, we have a strictly convex problem with a single unique solution. I'll let you check that. But for now, let's just look at a simple algorithm that does that. Before I do that, any questions on what passed so far? Okay, so we're going to discuss the algorithm, and we're going to try to give some motivation eventually later on why this does what we want on graphs with clusters, if we make it to that point. I'm moving a bit slower than I intended to, but I think it's good to just take it slow. Okay. I don't know. Math equations stress me out a little bit. I'm very happy after I understand one, but I'm stressed out. I find them very stressful. So I want to reduce it, at least for a few moments. I want to go to my happy space. My happy space is all about friends, or maybe because I'm a computer scientist, I don't have real friends, but I have these Facebook friends. You know, I get lots of them all the time. I'm always getting these invitations from Russia. You're so friendly in Russia. Also, I can get, a lot of Africans want to make me rich.
I know that.
Okay. So, but in general, we're maybe thinking about Facebook, and we're thinking about our friends, and we're thinking about maybe opinions. Like, you know, I don't know about you, but I don't have strong opinions in general. I'm kind of a little bit wishy-washy. At least, like, for instance, like things about politics. You know, I don't like politics. I don't know anything. I have a very strong opinion about my shoes, but politics, I don't know. Or maybe about what clothes are cool or not. I don't really have a strong opinion on. I'll just do whatever. But sometimes I wonder why I do what I do. You know, I know in cases of strong opinions, strong opinions are the things like nodes that I've circled in orange here, nodes with labels. These are maybe for us represent people with strong opinions. People whose changes aren't, like, I guess in the US this election's coming up. And maybe here I am over here. And there's Obama. This is maybe Obama. This is maybe Michelle Obama. There should probably be a link between them, but there isn't in this spreadsheet. Maybe this is like Michelle Obama's cousin or something. And this is Romney. And this is beliefs about who should be president. Romney very strongly believes he should be president. Obama strongly believes he should be president. So does his wife. And then there's a bunch of other people out there like me. Kind of like, opinion? Yeah, shoes. I know my shoes. I have strong opinions. Politics? So where do my opinions come from? Maybe they come, I enjoy telling stories, fake stories. I love to lie, basically. But anyway, maybe my opinions come from my friends' opinions, okay? Where are we going? We're trying to come up with an algorithm that solves this problem, and we're motivating it by this kind of simple idea that maybe opinions correspond to our neighbors' opinions. And we can make this sophisticated by having weights on the edges, like maybe I know some friends are closer to me and I respect their opinions more than other friends. But for now, just to make our life easy, I don't have any weights on the edges. So we might wonder, well, how does my opinion come about then? Well, there's unique individuals, labels, whose opinions are never going to change no matter what. Then there's other people whose labels are influenced by those around them. Okay, so initially, I and everybody else who doesn't have a strong opinion has no opinion. Then we're going to have an algorithm that works as follows. The algorithm is going to select a free vertex, i.e. one of these non-orange vertices, uniformly at random. This can be relaxed. It can be any sort of process you want that touches every vertex infinitely often. I just wrote uniformly at random because it's convenient. Average, and all it's going to do is it's going to look to its neighbors and take its average. It's going to say, well, what do you think, Joe? Should Obama be president? Well, I'm pretty got a strong opinion about that. Yeah. Obama, good guy, yeah. But then my other friend who knows Romney says, nah, Obamacare. Okay. So we'll take our opinion will be average bar away. Our friends' opinions weighted, okay? So for instance, here's somebody, and they know Obama, they know Obama's wife, and they know me. Well, the influence of Obama's wife is fairly strong, so he's leaning towards voting for Obama, but I'm kind of, out there. So 2/3 is their opinion. Okay. So now we choose another random vertex. Whoops. I'm choosing too fast. There I am. Okay, my opinion. Oh, yeah, I know Romney and I are close buddies. Here's this person. I take the average of -1, 2/3, 1, and 0. I do it. I get -112, and that's my opinion. And so on and so forth. I continue this averaging process. I average there. And this person's average is -112, 0, and 1. Now, one thing I've observed, once I've averaged here, this value is changed, will change because it's previously averaged. So, some questions we might want to ask ourselves about it. Does this process converge? Well, in fact, it does converge to the single global minima here. Let's think a little bit about this convergence, and that'll help us see how we solve this problem. Okay. But before I do that, let's have some fun. So play the same game I did before, and figure out what A and B converge to, and tell me why and give a justification. So, if you don't know how to, you can sit there and think about it abstractly, or you can be like me and just average things. So we put 0 and 0 for A and B. So I have a +1, and I have a -1, and I put in a 0 here and a 0 here. These are unchanging values. I'm going to keep averaging at random. 1 and 0 is a half. A half and -1 is 1/4, right? -1/4 divided by 2 is -1/8. Hopefully I did that right. -1/8, and 1 is 7/8 divided. I have a feeling I've done this wrong.
So it would be -1/4.
-1. Thank you. -1/4 and 1 is 3/4 divided by 2 is 3/8. 3/8 and -1 is -5/8 divided by 2 is -5/16. What will this process converge to?
2.
So why don't you take a moment to think about that. Don't say anything yet. Let everybody think about it, even though I know you know the answer. What will it converge to? Okay, if you know what it converges to and you're willing to answer and give a justification, raise your hand. Excellent. Please, what do you think it converges to, and briefly tell me why?
Converges to 1/3 and minus 1/3.
I must agree.
Good, that's a good start.
Yes.
You can do it as simultaneous equations.
Okay.
So it's good when it's converged, it's got to obey
Yeah.
A equals 1 plus B over 2 and B equals 1 minus A minus 1.
Excellent. So you can see that when this is 1/3 and this is minus 1/3, that somehow, that if we ever made it to those points, nothing would change anymore, because minus 1/3 and 1 is 2/3 divided by 2 is 1/3, and vice versa over here. Okay.
That doesn't exactly say why it does converge, but if it got to those
No,
points,
no,
then
no. Right,
it's stable.
right. We could write out the limit of these sequences, or prove something about the process as longer solutions, but I don't want to do that. But well, looking at these, you can get the flavor what it converges to, because I think if you look here, what's going on? Let's do one more. Minus 5/16 and 1/16 is that's 9/16 minus 9/16.
11/16.
11/32.
Yeah.
Okay, so we can kind of notice a pattern here. Suppose I add 1 to the denominator here, I get 11/33. 1 to the denominator here, I get 3/9. Add 1 to the denominator there, 1/3. Subtract 1 from the denominator, get minus 1/3, minus 5/16. Still not a proof, but you know.
Close enough
Me to
you
prove
just
things.
say.
Yes, nobody. You have to pay extra for the course. Downloadable content. Okay, but what's more, not going to exactly prove what we really want to prove, but we've claimed that this converges, and we claimed that converges to 1/3 and minus 1/3. What I want to do now is something lighter. I want to at least claim that it converges in some sense, okay? You can leave calling the squared norm, but I kind of like calling it an energy all of a sudden, because you start thinking, oh yes, energy decreases and converges. You know, if you think of this as a system of tension, whenever we take the average, you know, there's some tension between friends, and that tension is like an energy, and when my opinion becomes closer to my friend's opinions, it's reducing the energy between us. So I'm calling it an energy. So we'll call the energy induced by the squared semi-norm induced by the Laplacian. So the claim is, in that previous algorithm, if we look at the energy, just this term here, we're forgetting about we can either keep the weights or forget about the weights. The claim is, on every one of those steps, it must, well, it doesn't have to decrease, but it can't increase, okay? And so here we know that this is always bounded below by 0. Here we have a decreasing sequence bounded by some number, so we know it comes to some limit, hence it converges. Can somebody prove this step for me? Why is it whenever I do these averages that things decrease? How do I know that this is true? The claim is, whenever I do one of these steps where my opinion becomes the mean of my friend's opinions, the total energy goes down. You know, the tension between one edge may go up, but overall, if I sum up on the edges, it must decrease. Why does this energy, this semi-norm, go down after every averaging step?
So setting it to the minimum, it's the solution to the minimum energy by just changing that one value.
Yeah, so if we look at it, so when I, for instance, take the average at that location, each of these edges contributes a certain amount to the quote energy, or semi-norm. The energy that it contributes, the only thing involved in the averaging is exactly these three edges that are connected to that vertex. So these terms contribute the same amount. So then I just have to ask myself, well, what happens when I take the mean at that location? Well, what I'm doing is I have fixed values here. I'm taking the mean. What am I doing here? The mean is minimizing the square error on these individual things. As you've done a number of times, mean is the minimizer of the square error. So this contribution is unchanged. This one is set to the minimum it can possibly be. So every time I do one of those local averaging steps, I'm finding the mean of that square error locally, and I did that kind of fast, but I encourage you to check it. Okay, so convergence in energy. What I haven't proved for you, and a feature which I should have introduced a few slides back when I was introducing the norm and semi-norm, is I'm going to try to put the word technical on slides where I think this may be of some interest to people in the class, and it's worthwhile to think about, and it's very exciting. But you have a lot of classes full of very exciting material, and you're going to have to pick and choose probably. And so anything I put technical probably means that, well, it definitely means I won't examine it. Okay. So this is interesting, but I'm not going to explain it, and it's not going to be examined. But it's actually not so easy to prove that such a process actually goes to the minimum, not just in value, but at the point as time goes to infinity. So getting that proof right is actually subtle. Okay. I'm going to move a little faster. Okay, so maybe based on what we did then, if we want to solve this problem in general, we can use what we've done with least squares and other methods, is we can take the gradient of this and set it equal to 0. Okay? So we take the gradient of this and set it equal to 0. We have two kinds of equations. We get one equation which says at a given value, its value must be the weighted average of its neighbor's values. That's the first equation. And the other value corresponds to the values for the constraints. Okay? So if we want to solve this, and we don't want to do some touchy-feely method of talking to our friends and having a network of friends averaging everything, we could just use whatever sort of favorite linear system solver we have to solve this system. What I'm not doing for you, but maybe of interest to you, you can write this as a matrix equation for easier implementation in MATLAB in that format. See those matrix equations, see there's a reference given, the Zoo book, or C. Doyle and Snell, 1984, which is a fun paper. So thinking about what we're doing with this averaging method, what we're doing is we're not doing gradient descent, but we're going as far as we can in one coordinate direction until we can go no further in that coordinate direction. That coordinate direction is near the gradient, so we keep descending. Many efficient methods to solve linear systems. Not optimization, not going to discuss it. Consensus might be nice because, sure, for 1,000 things, for 1,000,000 things, well, 1,000, 10,000, 100,000, maybe you can use MATLAB on your system. But you start thinking of, well, can these systems be solved in extremely parallel large systems? Then maybe these methods where you average a single thing locally is efficient and it's highly parallel. In terms of reading the literature on semi-supervised learning, if I wrote this as a series of matrix equations and I did the updates simultaneously, roughly speaking, this would be called label propagation. Okay. We want to understand why things work. We know what the algorithm is. One can talk a lot about how things work. So in general, machine learning, you have ridge regression, you have support vector machines, maybe you have neural networks, maybe you have something else. So the question is why do you do these algorithms? Why are some algorithms, why do you use them? You want to give some reason why it makes sense for your problem. There's many ways that we can give reasons. We're going to give a light reason today. So what we're going to try to argue is that we're going to argue that we can view this graph as a network of resistors, and then if we label according to that, if we think of it as a resistive network, we're going to respect cluster structure, which is basically what we wanted to do. Another way to think about what's going on, which many people find insightful, is to think about this instead as defining some random walk on this graph or network. A method I'm not even going to attempt, justification I'm not even going to attempt to claim is, in some sense, I encourage you to look at the references, particularly by Belge and Nioki. You build these graphs, you get a Laplacian, you sample data in the limits of infinite amount of data. The graph Laplacian may approximate the Riemannian Laplacian from the data manifold, and there are lots of, I'm not going to tell you this story, but for those of you out there, this is a beautiful story which I encourage you to look at. Maybe next week we'll talk a little bit. There's many ways that you can give bounds to these kinds of algorithms, many kinds of predictive performance guarantees. We may talk or may not about next week some online bounds for graph problems. But the basic shared idea in 1 and 2 is going to be some idea of connectivity. That when we have this when we have our points, we're building our graphs, we use some similarity metric D to build our graphs. And that kind of gave us, that's kind of like our first approximation to knowing what distances are in the space. But then as we get a lot of unlabeled points, when we use the graph Laplacian, that's going to kind of warp this initial so-called ambient metric in the space to reflect the density of the points, because the Laplacian is going to somehow take into account connectivity. And so we're going to let the Laplacian warp the metric. That's going to be the intuition. Okay. Did I go too fast? Yes. Okay, simple interpretation of what we've done before. So we take this optimization. So we're going to think about this network instead of a network of whatever it was before, of a network of vertices connected by resistors. So you have some circuit with resistors. Labels correspond to voltage constraints. So for instance, in this network of resistors, we're imagining that there's some battery here that's maintaining a voltage difference of 2 between here and here, and a voltage difference of 2 in here. So these doubly black things correspond to constraints. Who here did electric circuits sometime in their education? Who's never done electric circuits? Okay. It's tougher if you haven't done electric circuits. You have to review some. But I'm not going to review it all. Okay. With a given labeling, we can associate a power to it, where power is like energy, but it's the heat dissipated, so power is energy over time. But just think of it using the energy metaphor before. And we label by minimizing energy, or technically we should say minimizing the power. When we hold these voltage differences here, and we solve this previous Laplacian problem, or we do that averaging technique, what we get here are the voltages that minimize the power. So this is, we can think about this as a network of resistors, and then we can see this optimization as that. Another detail I should add is that if we have weights on the edges, so if there's a large weight here, like we have a weight of 1,000, that's a resistance of 1,000th, i.e., if you have a large weight, things are more closely connected, so there's a little resistance between them, the metaphor. So the weights correspond to 1 over the values of the resistors on the edges. Okay. Questions? So this is exactly the result that we would have gotten from running the consensus algorithm. Okay. Let's add in another useful concept for us. Another useful concept, actually let's look at the picture. We can talk about the effective resistance between two vertices. So here we have resistors on the edges, okay? But now we can talk about, even though there's no direct edge between them, all these resistors are acting like some resistance between these two vertices, okay? And so what we call the resistance between two vertices is what I call what one calls the effective resistance, okay? So this is a very wordy, I would say, informal definition, that we could make it formal. So for a pair of vertices, the effective resistance between the vertices is the resistance of the total network when a voltage source is connected across them. So it's not the resistor on the edge, but it's how much it appears if we put voltage across them that it resists. From a physics point of view, it's the voltage difference needed to induce a unit current flow, 1 amp, between a pair of vertices. Okay. But well, I have pictures and something else. But effective resistance gives us something nice, which is going to make sense in our discussion of graph connectivity and the happy, friendly Facebook world, which I'm going to go back to for a moment. So let's look at this simple graph here. So here I have a very simple network, and some of you will know this because you recall things from, you've done some electric circuits, so you're very familiar with this. But here I have a graph. Here I have resistors 1 on each of these edges. In terms of, we all hear this thing of 6 degrees of separation. Maybe this is myself, maybe this is Massey, maybe this is Lady Gaga. I'm in geodesic distance, I'm 2 away from Lady Gaga. In terms of friends, like you're 6 degrees separated, I'm not doing so bad. So that's what I'm in geodesic distance, because that's just 2 hops. What about effective resistance? I say the effective resistance under the previous definition is 1. Why am I saying it's 1? Can somebody tell me how to compute that effective resistance as being 1? Maybe that nobody has done enough electric circuits, and I'll do it for you. But think about using resistors in series and resistors in parallel to argue this for me. A volunteer.
I have done nothing on electronics, but I would imagine it's 1/2 on each branch. So I think if each branch gives you 1/2 resistance, you manage to get the half amp through each branch. You get 1 in total.
From P to Q, you have 2 parallel circuits, each having 2 resistors.
Yeah, so if I got rid of one path, the resistance from here would be 2, because you know, it's like resistance adds as you go along a path, and it adds linearly. So it's 2. Good. Keep going.
But you have 2 parallel paths from P to Q.
So there's 2 ways to go. So it's like you're closer. There's more ways for things to flow. And so if you have 2 resistors, well, we'll write down the exact rule of things in parallel, then the effective resistance is
1 over R is 1 over R1 plus 1 over R2.
yes, 1 over that. Good. And so that works out if they're the same value as being half that same value. So resistor of 2, then we have 2 resistors of 2, then in parallel combined it becomes a resistance of 1. So if you're into Facebook as much as I, and you want to know how close you are to your friends in Russia, you can think of the effective resistance as the better Facebook distance than geodesic distance. So for instance, here's okay, here I am, and we already discussed that direction. Maybe this is David Barber, and this is
Lady Gaga.
no, Lady Gaga's here. Can't you tell? I thought I did a very good representation. This is Obama. I know David. I know Obama. Let's say each, everything's a unit for now. So I'm kind of distance 2 from Obama. But in some sense, I know Lady Gaga better because I have, I know John Shaw Taylor and I know Massey, and they each know Lady Gaga. And so I have 2 different ways I know Lady Gaga. So in some sense, I'm much closer to Lady Gaga than I am to Obama. So we can think of effective resistance as a way to measure distances on graphs. I'm going to let you answer, in a moment. And it can also turn out that it's a metric, i.e. that if I, all the obvious properties are going to be true, but the triangle inequality, the distance from A to B and the distance from B to C is always more than distance from A to C. I'm not going to prove that. Okay, what's your question?
For the geodesic distance,
Yes.
you just sum up the distances on the branches and then up there.
No, the geodesic distance is the length of the shortest path.
So it's the
Between-
shortest distance.
Shortest distance,
It
yes.
doesn't take into account.
It doesn't take
connections
account
you
the
have.
connectivity. That's why effective resistance is nice, is it incorporates connectivity. Geodesic is just counting the shortest path. So just to have a little test, in geodesic distance, I'm 2 from Gaga. I'm 1 in effective resistance to Gaga. And likewise, I'm 2 to Obama in both geodesics and effective resistance. So let's say this is all the graph there is. There's no other friends, because that would change the story. How far in geodesic distance is Gaga from Obama? 4. 1, 2, 3. Whoops. 1, 2, 3, 4. How far in effective resistance would you guess from 3? Yeah, we know this is 2. Somehow these are separates, so we kind of expect things to add. So it's 1 plus 2, 3. Okay, you're experts. Now, if I wasn't rushing, I could prove these various things from. You probably perhaps remember Kirchhoff's current laws that the current in is the current out. We can define the effective resistance by the voltage difference by the current. We also have the loop rule. We could use that to prove resistors in series. We could use it to prove resistors in parallel. Okay, this is the technical thing which you don't need to know, but if you're interested in kernel methods and things, and maybe if you take advanced topics is going to have more of a flavor of things of this type. In Arthur's half, from I know of Arthur. The effective resistance, let's do it fast. So if you have a norm, there's always a dual norm. The dual norm is the some set of functions on it. Associate is kind of dual to it. Okay, I'm waving my hands terribly. It's defined as false. So this you don't need to know, but you might want to think about it at some point. So likewise, for the Laplacian, we have some dual norm. It turns out that the effective resistance is the dual norm of the evaluation functional at P and the evaluation functional at Q. You didn't need to know all that on the previous page. You can think about it, and think about it in general for kernel methods, is that you always have a norm and a dual norm. You can optimize the primal and the dual. Beyond what I need today. One formula which, however, I do want you to know, which is kind of useful to think about. We can forget all about Kirchhoff's laws if we want to. We can derive all of Kirchhoff's laws, in fact. The only thing that we need to derive Kirchhoff's laws of all of electricity is that definition of power. That's enough. It's a variational approach. So we can, once given that, we could, for instance, define effective resistance as follows, and then define everything else. So the effective resistance will be the minimization of that norm with labeled constraints 1 and 0 and 1 over that. So let's look at another way to compute the effective resistance. Rather than doing this as an exercise, suppose we want to compute the effective resistance between A and D, and these are unit resistors. And this is 1 and this is 0. Well, you know from the previous story on the consensus that when we minimize, these are going to be roughly equal. So this will be 2/3, this will be 1/3. Okay? So what is the value of that when optimized? So 2/3 squared, 1 minus 2/3 is 1/3 squared is 1/9. 2/3 minus 1/3 is 1/3, 1/9. Same thing there. 1/9 summed 3 times is 3/9. 1 over that is 9/3. Thus we get the effective resistance. You can check the same story is true here in parallel. For instance, if this is 1 and 0, what do you think, doing consensus, we would converge to here at? If these were held at 1 and these were held at 0. We'd have to converge to a half, and then one change. We'd have a half here and a half there. Once more, we take the squared differences. We get 1 minus a half is a quarter. 1 minus a half is a half. Squared is a quarter. A quarter plus a quarter plus a quarter plus a quarter is 1. 1 over 1 is 1. You get. So it's another way, instead of using Kirchhoff's laws or trying to apply rules like series and parallel, to compute the effective resistance, and for us we'll use that as our definition of effective resistance. Okay. Theorem, which we won't prove. If you look at the pseudo-inverse of the Laplacian, we're thinking about how the kernel behaves. It gives you the effective resistance between two vertices by taking the two diagonal elements minus twice the off diagonal. There's a subtle point there which I won't make.
Who's that reference? What's the reference, KR93?
Oh, sorry, that's Klein and Randick. I'll write that down. Sorry. I can't remember the name of the paper at the moment. Okay. I'm going to tell you a little story about what you can do with the graph. Suppose you have your social network. Suppose you have you build your graph Laplacian. Suppose you put that graph Laplacian in MATLAB and you take the pseudo inverse of it. You can then use that pseudo inverse to nicely visualize certain properties of your social network, as I do in this example here. Okay. So here I've plotted some graph of, I don't know, 36 vertices. And they kind of fall into clusters of 6. And things are more interconnected within the clusters and less connected between clusters. Some random graph. Now, suppose you had some network and you wanted to think about its connectivity. One way to measure the connectivity of a network is, well, if effective resistance is a nice way to measure the connectivity between 2 points, perhaps a nice way to measure the effective resistance of a net, or the connectivity of a network, is to sum up all those distances. Okay? So under that definition, what would be the most connected network and what would be the least connected network, assuming there's no weights on the edges? What's the most connected network? What's the least connected network under this definition, but it would still make sense under other definitions?
The most connected has the least effective resistance.
Correct. And what network would that be?
Here.
The complete graph.
Complete graph, because whenever you add an edge, the effective resistance goes down, and it can't increase. We could prove that from that last that last equation. And so the complete graph gives us the minimum effective resistance. And so what's the graph with the least connectivity under this definition, assuming that the graph is still connected?
Circular graph or a line graph.
Line graph, perfect, perfect. So line graph, you can kind of plug it in, but it kind of like looks less connected. You want the minimum number of edges it can be to connect it, so it has to be a tree. And then you think, well, if you have a tree, kind of the thing where things are furthest apart on a tree is a line. Okay, so given the Laplacian, then how does this connect to taking the pseudo-inverse of the Laplacian? Let's go through it quickly. Well, we can also think about how connected an individual is in a graph. How connected is an individual in a graph? Well, one way of measuring is just its effective resistance to everybody else in the graph. You can read that off the diagonal of the pseudo-inverse of the Laplacian by, because the diagonal of the Laplacian is your average distance to everybody else in effective resistance. We've divided that by n. Why did that go off? My computer didn't go off. Oh, the system is powering down for some reason. Okay, so we'll forget the graph. Yeah, we'll look at the levels, and we'll forget the picture. But okay, so if you look at the diagonal element, the first term RV divided by n is that average resistance to everybody else. The second term is the total resistance divided by n squared. So that's the mean connectivity with an extra factor of 1/2. So the diagonal tells you how connected an individual vertex is, and then if you wanted the total connectivity, you could just add up the diagonal. But then what I've plotted here in grayscale is the lighter it is means the more connected it is, because it has a smaller diagonal. The off value is that. Okay, so there's a connection between the kernel and the connectivity and the effective resistance quickly. Next slide. I'm technically supposed to be done. Okay, I'm going to do this extremely fast. This is the minute version, even though this should be a long slide. Okay, I have these two cliques here on the slide. What I want you to think of in this page is, instead of cliques, is to go back and think about that picture of two moons. Okay? We've built some graph on these. Okay? Actually, I'm going to do this almost as a y. And I only have a few edges between them. Okay? Now it may be I want to know the label of this point here, okay? If I look at the label of this point here, maybe I have two labels. Maybe I have a label here, and I have a label here, okay? Now, in ambient space, I'm quite close to this label. And here, I'm apparently quite far away from that label, if I only had these two labels. But then, depending on the exact details, I give a fixed or a worked example with a clique, because I have extra connectivity here. Is you can imagine that I might be closer in effective resistance than geodesic distance. So the high level summary is that when you build a cluster with a graph-based method, clusters tend to have more interconnections. There tends to be fewer connections between clusters. So even if you're directly connected to another label, if you're indirectly connected within a dense cluster, it may be that your effective resistance is less than equivalently the geodesic distance, and thus you label like the cluster. So this is an intuitive account of why the Laplacian semi-supervised learning method might work in terms of respecting clusters on unlabeled data. And I'm out of time, though I'll take any questions, and feel free to leave at the same time.
All of these are in the Klein and the paper.
What?
Can we find all of these in the Klein and the paper?
So what can you find? Klein and Randick only prove this formula. I mean, they do some other things. They talk about why one cares about effective resistance distance. They're chemists. They're interested in measuring effective resistance in molecules and characterizing molecules, I think. But the best generic reference is the one given at the start. The PDF that you can download, Chapter 5. But it's not going to pull out everything you need to know of effective resistance. Maybe I'll give you some more. I don't think it will. It'll give references to papers.
Quick question. Can
Yes.
you do nonlinear dimensionality reduction using this?
Nonlinear dimension. Yes. So a standard thing instead of using P. So
Something
because-
like isomap?
Yes,
But
not isomatic, but yes, so this standard story is like focusing on working with the semi-norm, but thinking of things as a kernel, instead of using straight PCA, there's a kernelized version of PCA. So you can use a kernelized version of PCA with the Laplacian kernel to do some form of nonlinear dimensionality reduction. And if you look at the papers by Belkin and Diogi, they have a method called Laplacian eigenmap, which you can read about, which is very popular in practice.
Going back to that one, is the